Welcome, everybody. I hope you're having a great time at KubeCon Atlanta. I hope you got some coffee into you, because I know we're on the final straight of the first day, day 0. So hopefully, Junchen will keep everybody awake. So what's very interesting coming back here is, I was at a conference here 11 years ago for the OpenStack conference. Hands up anyone that knows what OpenStack is. Okay, we've got a good crowd in here. So back then, we were looking at the infrastructure layer. And our big concerns was around virtual machines, getting them off the ground, looking at our network or compute, and our storage. Fast forward a few years, and then we were more interested around the PaaS layer. So with Kubernetes and getting our applications out there, deploying our workloads and getting our workloads running. And thank you to ChatGPT, or maybe not thank you, we've now pulled AI out from the white coats and the labs around the world into commonplace. So today we're looking at how do we deploy our AI workloads along with our traditional workloads. But despite all these changes over the last, I suppose, 10 or 15 years, one thing has stayed constant. And that is cost and speed in response to what we deploy. So for the next 20 minutes or so, Junchen and I are going to look at how do we lower our costs and make our AI workloads more performant by looking at KV caching. So for the first half of the talk, Junchen is going to walk through what KV caching is and what are the enhancements or the great breakthroughs that have happened with KV caching. And then for the second half, we're going to look at, I'm going to walk through the LMCache community, which has taken some of the great research that Junchen and his colleagues have done in the University of Chicago and put it into an open source community called LMCache. So before I hand over to Junchen, just a little bit about myself. I work over at IBM. For the last 10 plus years, I've been working in the cloud native space. And for the last maybe 2 or 3 years, I've been getting more involved around AI workloads and inferencing, etc. So I'll just hand over now to Junchen.
Great. Hello, everyone. I'm Junchen Jiang. I'm an associate professor at U Chicago. And at U Chicago, I did research in large-scale internet systems for internet applications and, of course, also AI applications. And I lead a research group with all the PhD students who originally created this LMCache open source project. And I'm extremely fortunate to work with a group of very talented PhD researchers, who not only push forward the boundary of open source, but also had research products that make this open source project unique, as we'll talk about this later. And I'm also the co-founder of this company called TensorMesh. It's building a product on top of this open source project. Now, let's talk about a trend first. Okay, I think this is old news now. Everyone focused on inference rather than training, but it's worth to point out that it used to be training was the biggest workload in AI, but these days AI inference or model serving in general is the most important workload, and the trend is very clear. When you look at companies who really train models, there's just a handful of them in the world, but millions of applications or organizations will be running AI inference, and that's why AI inference is getting very, very important from a system perspective. Of course, for CNCF, that will be the most important workload in the coming decades. Now, not just the workload getting more and more expensive, more and more significant, it's also the system behind it getting more and more complicated, more and more complex. Okay, serving large language model is not just a simple running a large language, running a neural network that as simple as that. It's way more complex than this. Think about this. There has never been an AI application that's as popular as large language model. Okay, it has never been an AI application as pervasive, as ubiquitous as large language model. So that brings all kind of challenges that was unprecedented when people talk about traditional neural networks. Okay, now one particular very interesting trend in the large language model world is so-called long context inference. Has anyone have heard this term, long context inference? Raise your hand. Okay, so long context inference, truth to be told, is the key for large language model to be so useful in all kind of real-world environments. Okay, the large language model was successful not just because it's big, not just because it had remembered so much things from its training data. It's because of its ability to learn things from whatever you tell it to do. Okay, whatever you provide in the context window. You ask it to read a long document, great. The model will read the long document and learn things automatically from it on the fly. You want the model to learn things from a code repository, you just put the code repository in the context window and the model will read it. Okay, and you want the model to learn things from a video, from a bunch of videos, you just put the videos and the model will tokenize those videos in the context window and treat them as just as other inputs. That's the amazing ability for model to learn things on the fly. And that's what's causing the context or the input context to be longer and longer. And so everyone is good system engineers here. You all know if you give application developers something to fill out, they're gonna just abuse it. You give them a context window, they're gonna just abuse it. Okay, let's face it. Now, longer and longer context window means what? It means the model had to process more and more stuff before it even spit out the first output token. Before it spit out even one token for people to read. Longer and longer context means the processing delay, the so-called prefill or the time to first token will get super linearly longer, okay? And not just delay, but also cost, because every new token requires strictly more computation and super linearly more computation. And that's the real problem facing the industry these days. Every company will always face the first problem, how do I get the model to work properly? And the very next problem they face is these two figures, the delay and the cost issue. Okay, how do we solve that problem? Now, I'm going to just quickly switch gear to talk about this thing, KV cache. I'm going to explain why KV cache is so important, but let me explain what KV cache is. Has anyone heard about KV cache, this concept before? A lot of them. Okay, so KV cache is not like a new term to you, but think about it. So why KV cache, right? I bet half of you don't really know what KV cache is, but let me just give you a 10-second version. KV cache is simply model's runtime memory. If you give model a document to read, its information, aka attention information, okay? The attention information will be encoded in the KV cache. So the model doesn't have to read all from the beginning to the last token it generates in order to generate the next token. All it has to do is incrementally append new information to the KV cache that it has generated so far. Now, KV cache, by the way, is not a cache. It's just simply two tensors. And I know machine learning people just screw people around. They call it KV cache, but it's neither KV store nor cache. It's simply two big tensors. And these two big tensors will always be kept in GPU memory during the life cycle of a query. Basically, the model will repeatedly use that KV cache to refer to its previous memory to generate the next token. Now, why do I talk about KV cache here? It's an old professor talking about machine learning concept. This is not token machine learning concept. This is a very, very important concept. KV cache has two significant meanings. One, it keeps model's internal understanding. It's reusable understanding. It's reusable knowledge the model can readily reuse over time. Okay? And two, KV cache embeds useful information that indicates model's attention. Now, in this context, I'm going to only talk about the first one, the reusability of KV cache, because that's the focus of LMCache. But I'm just saying KV cache is a very, very important concept. Every system engineer should grasp. Now, talking about how KV cache helps. here is an example. Just imagine you have multiple users issuing queries to different LLM engines. Let's say these engines runs the same large language model, so some sort of some version of Llama 4 model. Okay. Now, each query needs a long context. Let's say the long context is a document, and the model have to preview, to process long context every time. It's been quite slow. You can see I have this spin wheel there and spinning wheel there, and that shows the things are getting slow. I mean, it's very slow. The problem here is, as you can see, as the model preview or process the long context, it creates that blue box, that blue cube. That blue cube is the 3-dimensional KV cache tensors. And now that tensor, you can see, is the same thing, as long as the context is the same. And in fact, in real-life workload, there are a lot of situations where the context is shared. Imagine if you read a long document, you won't read a long document just to answer one question. No one's gonna read a long document just to answer one question. Chances are the same context will be used over and over to answer different questions. Think about user chat history. Think about user shopping history. It's going to be used repeatedly. Think about news documents, right? It will be queried repeatedly. Think about code repository. It will be queried repeatedly for different purposes. Now, if you think it that way, you can say, why don't we just reuse the KV cache? Because like I said, KV cache is models runtime hot memory. It's reusable, so the model can directly skip the reading of context. Okay, that's what this animation is trying to do. It gives you the impression that this blue cube can be reused, and once you reuse it, everything can be faster, much faster. Okay, because the model can readily reuse its own memory. It's like you load people's memory, model's memory into its brain. It's like the movie Matrix. Okay, so the slogan here is you just preview once, you keep the KV cache, and reuse it over and over. Now, of course, good system engineers now will wonder, what's the system challenge here, right? So it's just slow data. But still, this is no easy feat. Think about what's the traditional LLM engine does, right? So in traditional ML engine, what it does is it keeps the KV cache in its GPU memory all the time. Why? It's because it can be used in the same life cycle of a query. Now, the funny thing is, all these engines are going to discard this KV cache when the query is done. So what we're trying to do with LMCache project is to keep it with whatever storage capacity you have in the system. As long as you have local CPU memory or local disk or some remote storage, you're going to keep it somewhere. Okay? And LMCache is the project to allow you to do this. And of course, you can think about with multiple LLM inference engines, the KV cache can be shared across these engines via Ethernet, via RDMA, via all kind of network connectivities. And finally, if you guys have heard anything called this thing called PD disaggregation, preview decode disaggregation, that's just another use case of KV cache sharing between engines, and that kind of sharing is cross GPU memory. Now, with all these requirements, you can almost think about a library, a unifying library that supports all these KV caching semantics, including GPU to GPU, GPU to CPU, CPU to CPU, and storage offload. Okay, and LMCache library is arguably the first and probably the widest deployed KV cache library these days in industry. Now, what's the challenges that we solve in this open source library? This is not just the open source, it's some code we open source just for the sake of having some functionality. It has more than a year of optimization, engineering optimizations, and I'm fortunate to have PhD students who can sacrifice their paper writing times to really optimize the system performance of this library. Now, one thing we did was to make sure efficiency is the highest. This is something Martin will talk about in a few minutes. And also, it has to co-evolve with inference engines. These inference engines changes all the time because large language models, open weight large language models are released almost every week. Okay, so these inference engines themselves have to evolve, and the KV caching library which is an ecosystem project, right? So working with the inference engine has to evolve as well. So how do we deal with the friction between these two projects? These two entities. And of course, KV caching is no longer just one transparent aspect. It has also many features that operators need to access. So for example, you can directly query where the KV cache is and so forth. Now, I'm not going to talk these things in detail. Martin is going to explain the details in a few minutes, but I just want to say these problems are the focus of our project. Now, to show the high-level overview, this is just a very, very high-level overview, okay? They don't have any technical meat here. It's just a router in front of all these inference engines, such as vLLM, and the KV caches behind those vLLMs. Okay, LMCache project, including LMCache project. Now, from ecosystem perspective, LMCache project, like I said, is the lowest level, just above hardware and storage systems, and it sort of links. It's a link between the hardware and storage with these inference engines, and it's being used by a lot of companies these days. Okay, so I'm going to hand up over to our valuable community contributor, actually one of the top contributors, Martin Hickey, to talk about technical details.
Thanks, Junchen. So we have about 7 or 8 minutes. I'm not going to go into all details because, first of all, we don't have time, and second of all, you'd be bored and you'd all be leaving. But what I want to do is just give you a bit of a flavor of what the community is, so that you can maybe look in, try it out and work around. So there's a QR code there. If you want to snap that, it'll bring you straight to the main repo. And as I say, go in there, have a feel around, see what you think. If you want to go to the website, it's LMCache.ai up on top, and you'll get all your links there to the demos, GitHub, examples, etc. And down at the bottom there, you'll see a link to a technical report. And this is a report that Junchen and his students have put together from, I suppose, all the technology breakthroughs and so forth they have done for this caching when you're offloading from the GPU and the different type of storage into storage backends. So as Junchen said, it's a library or a framework which gives you this caching layer. And this caching layer then manages that whole ability for the offloading of the caching, when it should store, how it moves it across from GPU to CPU, and any other workaround, we'll say the PD disaggregation and using things like Nixel, etc. for that copying and moving. It's open. It's got permissive license. It's part of the PyTorch Foundation. And as I say, go out and have a look and see what you think of it. And also, what Junchen said as well, it's that lower layer. So it's an attachment onto your inferencing engines like vLLM, SGLang, and hopefully down the line, we will be compatible with other inferencing engines. So what does it mean for you as a user? How is the flow and how does it work? So your key thing here always is that it's going to be when you make the prompt to the model. That's going to then, when it's going through its different activation layers, it's going to look at the tokens and say, first of all, do I have that token cached? If that token is cached, it says, right, I have a hit, so it's going to return it. So you don't need to do the recomputation then. Any tokens that are not already cached, then it's a miss, and it's going to have to do the recomputation. But as you can see here, that if you keep this ability to not have to recompute every time, you're going to make it far more performant. Your returns are going to be quicker, and hence you're going to bring your costs down. Then afterwards, once the response comes back to the user, in the background then it's going to make the storage of the different cache to the different backends that are configured. So what I'm going to look over the next few slides is what are the main components of LMCache. So one of the key components really is the cache engine. So that's the workhorse here. This is what manages its connections with its inferencing engines. It manages the different backends that it has, and it gets involved in how does it transfer the GPU tokens into the CPU and hence to the different backends that are enabled, so your disk and your different storage backends like Mooncake, Redis, etc. The connector here is what Junchen put up earlier is how do we provide that layer between the caching and the inferencing model, so that if changes happen in the inference model or new models come in, how does that work? And that's around the connectors. So the connectors give you that bit of space so that when changes do happen or whatever, all that logic can be inside in the connector layer, depending on what the architecture is of the models or how the data format changes. And then in the backend part then is around the transfer. So this is where are you going to store all this? So yes, it's going to go through the CPU offloading, but where does it go from there? And you can configure where you want it stored, because you're not going to be able to keep everything in, you know, we know with GPU memory to start with, but not in the CPU either. And what you persist and what type of eviction policies you use. So LRU, like last referenced policies and stuff like that. So you can also use FIFOs and stuff, but in this situation, it's mostly LRU. And then the other part then is around the idea of the worker. And the worker here really is its ability to go across different instances of LMCache, and also the ability to help you if you want to do your API for the management of the different caches. So the basic strategy is all around GPU to CPU and then to the different types of storage backends. So that's what this very simple diagram shows. So when we look at components, we talked about the connector, but two key components come here around the different type of memory, and this is where the optimizations come in. So the page memory that's used by inferencing engines are usually a very fine grained memory. And so what I mean by that is it's in small blocks, but that's not very performant and is very poor for latency when you want to do I/O. So for that, there is going to be conversions here where it's going to take that particular memory and convert it into, I suppose, the most coarser grained memory, so bigger type memory, so that it's more performant for storage and I/O. So what we're looking at here is the work that has been done around how to chunk that, and also the batching, etc., that has been done in the research by people in the community, some of the maintainers, and Junchen and his colleagues. The other part then is around how we index it and how do we get to it, so using hashing techniques and stuff there. And also then when we look at, this all has to be done asynchronously. So that's really important, that this should never ever block up the inferencing process, and also hold GPU cycles, etc. And then we have the connectors here, which we talk about. So this is configurable connectors that you can configure ones out of the box that we already provide, like Redis, Mooncake, etc., and S3. But also we have an ability here that you can extend it using the API and add your own backends. So in the cache and transfer, why I want to show this is that traditionally you might have looked at with the caching for after every activation layer. But some of the work that was done around, the research done around pipelining and so forth was, layer-wise pipelining was that you can take this technique where it can be broken down into multiple activation layers, and the parts of them can be done in parallel. So they can be executed in parallel simultaneously, and it can be done in different processors and devices. So that ability to do that every time a request comes in, that the inferencing engine can call it, and that work happens then for this technique. And that then again is a big part of the performance around that. Excuse me. And the last part here is around your ability to be able to manage your caching. So how can you find where your different caches are? Can you move your caches around? Can you delete those caches? So this is very important for probably different iterations you have, different calls you do to the model, and then similar type calls. Can you reuse some of that memory? Okay, here's a couple of resources you can have a look at. I recommend check out the documentation. Like every open source project, that's the first place always come in. If you find any issues, raise issues, push PRs. We're always looking for excuse me, for contributions, etc., from the community. Check out the other documents as well, and I'm just going to finish up now. Okay. At the start of the talk here, we talked about the way workloads have changed over the last number of years. We now have AI front and center, and it's a new workload we have to be able to handle. Initially, we thought of this of how we tune models, but we now realize that there'll be only a certain amount of excuse me, companies that are going to tune. It's going to be down to inferencing, because that's where the value is going to be. But we've realized too here that there's a cost, and there's also potentially a delay when we call different models, and we especially see it around agentic, etc. So that ability to be able to bring down cost and to be able to improve the response time is always key to how we use technology. And KV caching is the way is the way forward in this, and LMCache is the standard bearer. So thank you very much.
Yeah, I don't think we have time for questions. Yeah.
So reach out to us over the next few days when we're walking around in the hallway track, or come on down to the LMCache booth at the showcase. Thank you very much.